Welcome to Introduction to Structures. This will be problem 8, moment of inertia for a T-section. So in previous videos we have covered a moment of inertia for an I-section and a moment of inertia for a non-symmetric cross-section. But this problem of a T-section is an intermediate problem in terms of complexity, so it's a good example to follow and to learn how to determine the moment of inertia of a non-symmetric cross-section as the T-section. But to start, let's just remember the formulas for the rectangular cross-section. So the barycentric moment of inertia of a rectangular cross-section with base B and H is equal to BH cubed divided by 12, as you can see on the screen. And the moment of inertia regarding the axis, vertical axis and barycentric axis YY is equal to HV cubed divided by 12. It's necessary to remind these formulas because these formulas will be useful to calculate the moment of inertia of a T-section. Remember as well that because the T-section will be formed by basically two rectangles, the moment of inertia that we will calculate are regarding axis parallel to the barycentric axis of the rectangles. So we will need to apply this principle of this formula that says that the moment of inertia for a rectangular cross-section regarding an axis parallel to a barycentric axis like XX, for example, so I'm referring to the axis AA in this case, is equal to the barycentric moment of inertia of the rectangle plus the area of the rectangle multiplied by the distance between the two axis, the barycentric axis of the rectangle and the axis we are using to calculate the moment of inertia, and this distance has to be square, as it says in the formula on the screen. So now we are ready to study then in which way we work with a T-section. A T-section is called T-section because the shape of the section is like a T. So this beam will have them a flange, which is a rectangle on top of the cross-section, and we have a web, which is as well a rectangle in the area that I'm showing on the screen. So this T-section will have a centroid that will be at some point on this axis of symmetry YY. So we know part of the location of the centroid for this cross-section, but what we need to determine is at what distance from the base or from the top of this cross-section is located the axis XX, which will be the barycentric axis that will cross the centroid G of this cross-section. So in order to determine that position, we will have to do the summation of moment of areas. So in order to simplify the calculations, it's a good strategy to divide the cross-section, the T-section, into rectangles. So we are going to work with the flange, this green rectangle, that will have an area, a base, and a H, and a location of the cross-section in the middle of the rectangle. And we're going to work as well with the second component of this cross-section, this rectangle in black, which will be the web of the cross-section, and will have as well an area, a base, a H, and a centroid, as well as is located in the middle of the the black rectangle on the screen. The moment of inertia of the T-section will be in between these two centroids of the rectangles that form the T-section. The distance from one to another will depend on the areas of these rectangles. So if we make an example, let's say we have this T-section with the dimensions you can see on the screen. What we need to determine in the first place is the area of the of the flange on top in green. So the area will be just 120 millimeters times 30 millimeters equal to 3600 millimeters square. The area of the web will be the base 20 multiplied by the height 130 all in millimeters. So the area of the web will be 2600 millimeters square. The total area of this T-section will be the summation of the two components, the two rectangles in green and black. So very simply will be 6200 millimeters square, the total area of this T-section. These values will be useful for writing the formula that expresses the summation of moment of area, as we are going to see in a moment. So now what we need to determine before writing the moment of the areas of these components of this section is to realize what are the distances between an auxiliary axis we are going to use to locate the centroid. So we're going to define this axis of reference at the bottom of the T section in red, and we are going to refer to this axis the distances to the centroids of every component of this T and the location as well of the centroid of the T section. So the T section will have a centroid that we don't know at the moment exactly where it is, but we are going to call this unknown YG. So it will be the distance between the auxiliary axis and the barycentric axis of the T section. What we know at the moment is the location of the centroid for this web in black, which is in the middle of this height 130, and this is the reason why this distance y2 is equal to 65 millimeters. And we know as well the location of the centroid of the flange in green, which is in the middle of this height 30, so 130 plus 15 is going to be 145 millimeters, the distance from the auxiliary axis to the center of the flange of this T section. Having these distances, we are ready to apply this property we use to locate centroids in a cross-section that are formed by several rectangles. So we are going to say that the total area of the cross-section, so the total area of the T, multiplied by the distance to its barycenter from the axis of reference we are taking, is equal to the summation of the moment of area of the flange multiplied by the distance y1 plus the area of the web multiplied by the distance to its barycenter to the axis of reference y2, which is 65 millimeters. From there, we are going to work out the distance yg, which is the first problem we have in this cross-section, the location of the centroid. Simply moving this factor in here to the left member to the right member, dividing all the member to the right. So expressing this last formula with the values of the exercise on the screen. So 3600 is the area of the flange multiplied by the distance from its barycenter to the axis of reference, plus 2600, the area of the web multiplied by 65, the distance to the axis of reference, and all of this divided by the total area, 6200, of the T section. All of this give us 111.5 millimeters approximately. I have rounded to the first decimal, and now we know exactly where is located this barycenter of the T section. So YG is equal to 111.5 millimeters. Now we know the location of the centroids. What we need to work out are the distances from the centroids of every rectangle, for the flange and for the web, regarding the axis, the barycentric axis of the T, because now we know where is located exactly. So we know this distance 111.5. We know the dimensions of every rectangle and the T section, so we can work out easily the distances from the barycenter to the barycentric axis XX. So this distance in here from this centroid to this axis is 33.5, and the distance from the barycenter of the web, or the center of the wave, to the axis XX is equal to 46.5. Having these distances, we are ready to start the calculation of the moment of inertia regarding the axis XX, which is the barycentric axis of the T section. The first terms of this expression in green in here is the barycentric moment of inertia of the rectangle in green. So it's just base times h cubed divided by 12, which is 120 times 30 cubed divided by 12. But we need to add the moment of inertia regarding the axis x, which is parallel to the barycentric axis of the rectangle. So we need to add the area, 30 times 120, multiplied by this distance, 33.5 square. So these two terms in here are the contribution to the moment of inertia of the T made by the flange. If we consider now the web, the first term in black in here is the barycentric moment of inertia of the web. So it's the base times 130 the h square cubed to the divided by 12, plus the area of the web, 20 times 130 multiplied by the distance from the centroid to the axis xx, the barycentric axis square, as is shown on the screen, and the value of this moment of inertia is 30,593,617 millimeters to the 4. Of course, I have rounded this value, not to use decimals, because the decimals are not significant for quantities of this big. So, if we need to calculate the moment of inertia regarding the other axis, the axis YY, the advantage is that the axis YY is a symmetric axis, so it's symmetrical regarding the t. So and this will make the calculation easier because the centroid of the t is in the same axis, on the same axis as the centroid of the flange and the web. For this reason, the contribution of the moment of inertia regarding YY of the flange is simply the barycentric moment of inertia of the flange, which is 30 times 120 cubed divided by 12, and the contribution of the web is just the barycentric moment of inertia of the web, because the barycentric axis of the rectangle is the same as the barycentric axis of the t. So it's going to be 130 times 20 cubed divided by 12, and the total moment of inertia regarding the axis YY is 4,406,667 millimeters to the 4. So again, I have rounded this value to not to work with decimals. So as a resume, so the total area of this section will be 6,200 millimeters square. The location of the centroid will be on the axis YY, and the axis XX will be located to 111.5 millimeters from the bottom of the dissection. The moment of inertia regarding the axis, the barycentric axis of the t, XX will be 13.5 millions of millimeters to the 4, and the moment of inertia will be 4.4 millimeters to the 4, as is shown on the screen. And that's it.